All right, we do have a daily check-in, but that's pretty much all we're doing online for right now. So after your daily check-in, you can just close up your laptop. We don't really need it right this second. So go ahead and do that. I'm gonna shut the door. Again, we do want to have a paper pencil out today for a quick note. All right, welcome back, everybody. Again, if you would do the daily check-in, we can put away our laptops. We don't really need them today. We will need them later for the assignment, but you don't need them right this second. I would encourage you to have paper and pencil. We are going to do some learning checks today and problems together. Encourage you to participate and do that stuff real quick. So again, real quick, do that learning check, and we can go ahead and put away the laptop. Today we're going to be talking about a very, very big and important chemistry topic, and it's really going to lead us to the rest of the year. We're talking about reaction. We said that like chemical reactions are like recipes, cooking recipes. You start off with this stuff, and you make this stuff. Chemical reactions and chemical equations are not equal signs. Just like when you're baking a cake at home, okay, the cake is no longer flour and sugar and eggs and that stuff. It is something different from what you started with. And so the same thing happens in chemistry. We were balancing chemical equation. We were putting some numbers in front of the equation. Again, talking about it like a recipe, like 2 parts of this plus 3 parts of this will make 4 parts of that. Okay, and making sure that everything is balanced in the end, because we cannot create nor destroy matter, even in chemical reactions. Even when it looks like we're destroying matter, even when it looks like we're destroying that cotton ball from last week, we still are not really actually destroying the atoms themselves. They're just changing. They're turning into smoke. They're turning into carbon. The black cotton that was at the bottom, that is carbon, okay, from the cellulose. So today we're going to be talking about what are those coefficients and from a chemical equation. And those coefficients mean something. So in the cooking recipe, you typically know of things like tablespoons and cups and gallons and liters and teaspoons and all those type of things. Right? And those are just a unit that humans made up. They said, this is going to be a teaspoon. This thing that we made. Scoop 1 teaspoon. It's not, an actual physical law of the universe type of thing, right? So same thing with a cup. Like, this is a cup. Anything about a foot, a measurement, again, it's literally somebody's foot. I think it was King Edward or King Charles, one of the kings of France. They measured his foot, and that became the foot. That's literally what it was. Okay. The yard is actually a wingspan. That's about a yard, but almost 3 feet. So all these measurements are human qualities, human aspects that we put to these types of recipes. Today we're going to talk about the chemistry one. And again, this is a human aspect. This is a human measurement of how chemical reactions occur. And the unit we're going to be using is the word mole. M-O-L-E, the mole. And yes, the mascot for the mole is a mole. Hence these little two pictures here. Whereas a teaspoon is a certain amount of stuff, a mole is a certain amount of atoms. And it is a really, really large number of atoms. It's 6.02 times 10 to the 23rd atom, or 4 molecules. So we talked about, like, we draw in a little picture about them colliding together, the atoms hitting each other and stuff. In a chemical reaction, we're not talking about 1 or 2 atoms hitting each other. We're talking about an astronomically large number of atoms that are colliding with each other, and then they're making an astronomically large amount of product when it is, 1 or 2, moles that we're talking about. Okay. So the mole is a counting unit, and it was derived by a scientist by the name of Amadeo Avogadro. If you know a little bit of chemistry, you probably heard of Avogadro's number. And Avogadro basically wanted to know how many atoms are in this much of whatever, right? And essentially he took a balloon of helium, and he wanted to know how many atoms are in this balloon of helium. Well, it turns out it's a big number. Atoms are small. You can put a whole bunch of atoms in a balloon, right? And it turns out that, it's about 6.02 times 20, times 10 to 23 atoms are within a certain volume of these gases. And so what Amadeo Avogadro did was he got some hydrogen. Hydrogen is on the periodic table up there, and it's super easy to make. We can make hydrogen very easy. You can capture it, you can find it, you can get it. And so hydrogen's very easy element, very easy gas to make. And he wanted to know how many atoms are in 1 gram of hydrogen. That's a nice easy number, right? 1 gram. And we kind of knew the idea of grams back then. Again, it's a human made up thing. But this is 1 gram, whatever this is. How many atoms are in 1 gram of hydrogen? Turned out there's 6.02 times 10 to the 23rd atoms and 1 gram of hydrogen. And so this is where this number is coming from, and where that number is coming from, up there on the periodic table, is this number of atoms weighs that many grams for each individual element. Okay. So how big is the mole? How big is 6.02 times 10 to the 23rd? If you had soft drinks, if you had 6.02 times 10 to the 23rd soft drinks, if you had a mole of soft drinks, it would cover the earth in a depth of 200 miles. That's a lot of soft drinks, 6.02 times 10 to the 23rd soft drinks. Okay. If you had an Avogadro number, same number, of unpopped popcorn kernels, and you spread them across the United States would be 9 miles deep in popcorn kernels. Again, it's a huge number. It's a really, really big number. Okay? If you were to count to a mole, and you decided to say, hey, we're gonna do 10 million every second, it would take you 2 billion years just to count to a mole. Again, it's just a really large astronomical number because atoms are really, really small. If you had a mole of moles, the little furry animal crawling in the ground, that would be about the size of the moon. A big giant meatball, furry meatball, the size of the moon. A mole of moles. So 6.02 times 10 to 23rd mole. So again, it's a really large number because atoms are really small. Okay? How long would it take you to spin a mole? If you spent $1 billion every second, it would still take you 19 million years to spin this number of dollar bills, or actually $1 billion every second. So again, just trying to put this into your brain here that when we're talking about chemical reactions, if I have one reacting with one, it's not just one atom, one molecule. It's a huge number of atoms and molecules. Okay. So again, where did it come from? Essentially, especially back then, he did what we call the Millikan oil drop experiment. A little bit of history here. You can actually put a drop of oil on water and use a microscope to actually see the interaction of atoms between water and oil. They don't like each other. Water and oil don't like each other. And so you can actually put that on there, look in a microscope, and you can see the atoms, the molecules of water interacting with the molecules of oil, and then see, calculate how many molecules are we dealing with. And again, it's a huge number. It's a huge number of molecules are interacting with each other in that situation. Okay. And no, they did not sit there and just actually literally count how many are there in there. They took a sample, and then they multiplied by, a portion. So for example, if I had the world's largest pizza and I want to know how many pepperonis are on it, I would take one slice, count how many pepperonis there are, and then say, well, there are 500 slices. So the one slice times 500 would give me a general average of how many pepperonis there are. Do the same thing with this oil drop. You can count how many molecules within a little part of a sample, and then expand that, by how many samples you have. Okay. So, real quick learning check here. Let's say we invented a new collection, new measurement called a rack. One rack contains 18 objects. 18. So question one, how many paper clips are in one rack? 8. 8, right? One rack has 8 objects. So there's one rack of paper clips, there's 8 paper clips. How many oranges are in 2 racks of oranges? 16, right? How many wraps contain 40 gummy bears? So you do go backwards on that one, you divide on that one, right? The 40 divided by the 8 will give you the 5 on that. So just like eggs or donuts, if you're buying a dozen, that's a made-up number, 12. Why 12? I wish they used 10. It would have been a lot easier for everybody. Okay? But they use 12 because that's the number they wanted to use. And then, of course, you have this idea of the baker's dozen, which is 13, which is like, why do we have that? Again, it's a human measurement. And so is the mole. The mole is a human measurement. So 1 dozen cookies equals 12 cookies. 1 mole of cookies equals 6.02 times 10 to the 23rd cookies, which is a lot of cookies. 1 dozen cards equals 12 cards. 1 mole of cards equals 6.02 times 23rd cards. 1 dozen aluminum atoms equals 12 aluminum atoms. 1 mole of aluminum atoms equals 6.02 times 10 to the 23rd aluminum atoms. Okay. Note that the number is always the same, but the mass is very different. Okay, the mass of 1 mole of cars is going to be totally different than the mass of 1 mole of aluminum, or 1 mole of the cookies. Okay? And that's what we're going to work on today, is figuring out the masses here. Okay, the mole is abbreviated. It's only 4 letters long. It's abbreviated MOL, which is saved me a split second not to write that E on there. Okay, but that is the abbreviation for the mole when you see it written out, MOL. Okay. So 1 mole of carbon is going to equal 6.02 times 10 to the 23rd carbon atom. 1 mole of water equals 6.02 times 10 to the 23rd water molecule. 1 mole of salt equals 6.02 times 10 to the 23rd salt molecule. It's not really a molecule, but on there. Okay. So if you break that down, that gives you a different percentage of sodium and chlorine atoms on there. So what we're going to focus on today is called molar mass. You guys have seen these numbers up here on the periodic table, and they are the atomic masses. But today we're going to be focused on the molar masses, which are using those numbers up there. So the mass of 1 mole in grams, okay, is going to be equal to the numbers you get on the periodic table, the average masses, okay, you get from the table. So 1 mole of carbon, so 6.02 times 10 to the 23rd atom, 1 mole of carbon equals 12.01 grams. So that's what the periodic table tells me. So when I have a chemical reaction, I say 1 carbon plus blah, 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 that's really 12 grams of carbon. So when I write out a balanced equation, I say 1 carbon plus this plus that, make this. That 1 carbon at 1 mole is actually equal to 12 grams. So when I do a chemical equation, a chemical reaction, I want to measure 12 grams of carbon. Okay? 1 mole of magnesium atom is equal to the periodic table, 24.3 grams of magnesium. Note that the mole is not changing, 1 mole, 1 mole, 1 mole, but the masses are changing because they have a different number of protons, neutrons, electrons. We know that already. 1 mole of copper on a periodic table, 63.5 grams, etc. Now, other things you kind of need to know the definitions of is molecular mass versus molecular weight. Okay. We all know the atomic mass. The atomic mass, atomic weight is up there on the periodic table. The molecular mass and molecular weight, which is what we're going to do today, okay, is you adding up the entire formula and figuring out what is the mass of this molecule. Okay? So that gives you the formula mass, or the formula weight, is that when you end up with the formula, so I have H2O. Well, I need to add 1 plus 1 plus 16. That gives me 18. That is my formula mass, my formula number. And again, you're going to hear all these terms. They all mean the same thing. They all mean 1 mole of those elements added together. Okay? Which is what we're going to do today. So real quick, look at the periodic table. What is 1 mole of bromine atoms? How much does 1 mole of bromine atoms weigh? And we normally do round to the near 10th place. However, and you math kids probably know this already, never round until you are 100% done. If you're adding 10 numbers together, you round the first one, you round the second one, you round the third one, you round them all, your final answer is going to be way off because you rounded. Add up all the numbers, then round the final answer. So if you look at the periodic table, bromine is 79.7 grams. That is 1 mole of bromine. So if I was doing a reaction and I needed to balance my equation, it said 1 bromine. It's not 1 atom. It's not 1 compound. It is 79.9 grams of that, which is actually quite a bit. So what's 1 mole of SN, which is 10? Okay. All right, so what's mass of 110 SN, 1 mole? 118.7 on the periodic table. So again, if I was doing a reaction, I don't want 1 gram, I don't want 1, atom, 1 molecule. I want more than that.
Wait, what number is it?
Okay.
Where is it again?
So 10 is it's underneath carbon, SN. 10. 118.7. Underneath carbon, so it's 4 down on carbon. That is 10, by the way. TIN. That's a Latin abbreviation, which I don't know what it stands for, but that happens a lot. All right, so kind of getting what Logan was asking here. The molar mass of molecules and compounds, all you do is you add up those masses that match your formula, and then that is your ingredient, that's your recipe for 1 mole of that compound. So for example, how much is 1 mole of calcium chloride, CaCl2, how much do I need to measure? How much do I need to weigh out? Well, I need to figure out what 1 mole of Ca is. 1 mole of Ca is 40.1. And then I need 2 moles, because I have 2 in the formula, right? So Cl2. So I need 2 moles of Cl, which is 35.5 for each one. That gives me 70, or, all right, yeah. Okay, that's a different problem. But anyway, so that gives me 71, plus the 40 will give me 111.1 grams per mole of calcium chloride. So if I have calcium chloride in my reaction, and it says 1 CaCl2, again, that's not 1 atom, it's not 1 molecule, that is 111.1 grams of calcium chloride. So I would get into my closet, get out my scale, I start weighing out what I need, and I do my reaction. Okay? So again, the reaction is like a recipe, and those coefficients in front are moles. They're not cups, they're not tablespoons, they are moles. All right, so real quick on your own, and on your piece of paper. Well, never mind. I already gave you the answer, I think. Yeah, I already did. So N2O4, if I look at the periodic table, nitrogen weighs 14. I need 2 of them though, so that's 28.2, or 28.02. Oxygen has a mass of 16, I need 4 of those, that is 64. So 64 plus the 28 give me 92 grams. Okay, so again, you're just adding up those numbers that match the formula. I need 2 of those, 4 of those, 10 of those, whatever it is. Okay. All right, so that is all we need to do for today. We are going to do a little bit more later. So today, we're going to be finding out molar mass. So if you guys go to your worksheet, now you can get laptops back out. But you are going to need paper and pencil. You're going to do this on paper.
Is this a theory or has it been proven?
What's that?
Has it been proven that there's that many?
The unit is gram per mole.
Yeah.
When you add them all together. So that many grams in 1 mole.
Has the number per moles been proven, or is that just a theory? Like that there's that many? Like you can't prove that, can you? Because it's such a large number.
Right. So, right. Yeah, the 6.0. Yeah. That's a good question. There is, we're not going to measure 6.02 times 10 to the 23rd molecule. So we need to use something we can measure like grams. So if I want that many molecules, I will convert it to moles by using those numbers up there. Now, I can measure that much that quickly. So for example, we have all right, so I got water. I can do this with any compound. So I have water. So my question to you would be, how long would it take me to measure 6.02 times 10 to the 23rd molecule of water?
You wouldn't know.
Not quite. I'll do it right now. Done. So this right there, I think, let me double check my math. This right there is 6.02 times 10 to the 23rd molecules of water. How do I know that?
You don't, like, that could be inaccurate.
Well, I mean, I'm not doing it super accurately, but this is very, very close to 6.02 times 10 to the 23rd molecules of water. Because I know the mass of water. What's the mass of water? The mass of water is H2O. So 1 plus 1 plus 16, which gives me 18. This is what I put in there. And the density of water is 1 gram per 1 milliliter. So I know that if I put 18 milliliters in there, I have 18 grams of water. 18 grams of water equals 1 mole of water. 1 mole of water equals 6.02 times 10 to the 23rd molecules of water. Now, am I exact on there? Obviously, no. I mean, I don't know if I'm exactly 18. I'm actually a little bit off, but that is where, so again, it doesn't look like that much water, but that is a huge number of water molecules just in that little 18 milliliters. And a huge number, Avogadro's number, 6.02 times 10 to the 23rd. So we're not going to measure exactly that many molecules. We're going to measure milliliters or grams. So again, this is grams. This is 18 grams of water. And because it's a liquid, I have to measure it by volume. I could do that with salt. I could give you 6.02 times 10 to the 23rd grams of salt in just a couple of seconds. So I know the mass of salt. Salt is 23 plus 35, 58. I would get out my scale, pour 58 grams. That is 6.02 times 10 to the 23rd molecule of salt. So I hope that makes sense. Did I answer your question? No. Okay.
How do we know that it's a bunch of zeros? It could be a bunch of other numbers. We can't ever count that often, like in our lifetimes. It's $405.
Right. You would not measure, you would not like set up the reaction to have exactly that many. Like
after the 602, it could be all nines.
Right.
And then it'd be closer to 6.
Yeah, so you're 100% right. So I would never try to actually figure out exactly how many molecules I have in there, but I would use a made-up measurement to do. I would use a made-up measurement of mole, and mole represents this. So this represents 1 mole of water. That's a human measurement, and that's why we would use grams, which is what we're going to do today. We want to figure out the grams for it. So yeah, so it's a chemical recipe. We're cooking with grams. We're not cooking with molecules necessarily. So you'll never know exactly how many molecules you'll have. Even the mole. I think Corinne wrote out every single number on there. Even the mole, it is 6.02 times 10 to the 23rd. I don't know the accuracy or precision, like how far it goes. You could probably look it up on the internet. Of Avogadro's number, how many decimals they give you, but even that number is not that precise because again, you're never going to literally count that many. So what they did in order to figure that out, as I kind of did with the pizza, is they took a part of the sample, figured out how many moles are in that, or how many molecules are in that, and then multiply that by the sample size, which is what you do with any big number. So today we're going to calculate the grams of different molecules, and where was it? And we want to use this worksheet here for today. And again, this is what we really care about as chemists, as scientists. When we do a reaction, we want something I can measure. I want teaspoons, I want cups, I want gallons, I want something I can measure. I can't measure 1 molecule. I can't measure that many molecules. Right? I want something that we can actually use. So we're going to use grams because that's a reasonable measurement and figure that out. So what I need you to do on paper, show your work. If you can show your work on a computer, that's fine. Just show your work, okay? You're not going to get credit without showing your work. Preferably on paper, though. Use a periodic table, and there's a link to a periodic table there. All right. There's a video if you need to know, if you need to watch how to do this. I just did a lot of it. But there's another video if you want to know how to figure out more math. There's a link. So what you need to do is you need to, I mean, it's simple. Just add up those numbers at that formula. And then that will tell you the amount you need to measure for a reaction. Okay? Now, Logan asked the very first one, is it carbon and iodine or the Cl? That's a very honestly good question because it very well could be carbon and iodide for all we know. Probably wouldn't be based on connecting the dots of the fluid dot structure. Probably would not be carbon iodide. But that's chlorine gas, Cl2. So that's chlorine, we're going to add 2 chlorine together. All right, the other one, pretty straightforward. Again, even for number 4, that is chlorine. Number 6, that is chlorine. Number 15, that is chlorine as well. So again, just showing your work, add up the atomic masses to get the molar, the molecule mass. And again, that will give you your recipe. That will give you your ingredients, the amount. That's all I have for you guys today for my part. I will definitely answer any questions you guys have. Please don't struggle with this. As you guys probably know, there's a lot of stuff going on this week, especially for juniors. We have the resiliency poll. Have you guys taken that yet? You guys been in your career class yet? Have you guys been in engineering yet? So you wait a minute, actually I don't think you guys got to do it. It's only freshman, sophomore, so maybe not. But you guys have your test on Friday, right? Your proficiency exam.
That YLP is on Saturday and then dual credit classes on Sunday.
Yeah, then I think a lot of finals next week for all your dual credits, most of them, some of them, all of them. So you guys have a busy couple of weeks coming up. Next week is actually, there's nothing really going on except for dual credit finals next week. That's good. And then you guys have YLP presentation? Saturday. Yep. And then after that, we have state testing after that week. And then, I don't know, we got stuff going on like crazy. So the weekly schedule is going to be very flexible. I do want to try to get labs in there just to have a little bit of fun in chemistry. So bear with me on that. We'll try our best to get as many labs in there as we can. So, all right, that's your work for today. You can see my example, how I got my final answer, just adding those numbers together. And again, that's what I measured here. I measured to 18 grams approximately. 18 grams of water, which is 18 milliliters of water, and that is 1 mole of water. And so if I had a chemical reaction recipe, and it said 1AC, so I don't know. Let's just do that real quick. Let's just write up a chemical equation real fast. So we're not really going to do this later. So you guys at home, hopefully you can see my board, okay? Let's say I have, I got to think of a reaction now. Let's just do a simple one. Okay, that's almost. This is what we did. This is what we did a couple weeks ago with magnesium oxide. Put the magnesium in there and caught it on fire. So if we have this here, it's not balanced. I need 2 oxygens. some more markers. Can you guys online see this? Running 2 oxygen there. That's going to mess up my magnesium. So this is my balanced chemical equation, right? So this is not 2 magnesium atoms. This is not 2 magnesium molecules. That is 2 moles of magnesium. And 2 moles of magnesium is that number on the periodic table times 2. So 24.3 times 2, which is 48.6. Plus oxygen, I need 2 of them. 16 plus 16 is 32 grams of oxygen. And then that is going to make this exact ratio here. That is going to make 0.6, 0. That is going to make 90 grams of magnesium oxide. But again, I'm not going to lose, I'm not going to gain anything. That's the conservation of mass. And so this, especially this right here, this is my ingredients. I need to go and weigh out 48.6 grams of magnesium, react it with 32 grams of oxygen, and then I will get a product. And we can actually test that, and we actually do the lab itself. We can do the lab itself and actually measure, did we do a good job with that reaction? Okay, so these are my ingredients. Again, it's not 2 molecules, it's not 2 anything else. You know, it is 2 moles, which are those numbers on the periodic table. I got to add up. Hopefully you saw that. Okay. So does that kind of make sense why we want moles and grams?
Yeah.
Now let's say I went back in my closet and I didn't have 46 grams or 48 grams of magnesium. Okay? I could half that recipe. I could 1/10 that recipe. I could 1/100th that recipe. I could make that recipe smaller. I could also make it bigger. Let's say I want to make a product and I want to have 180 grams of product. I could double my recipe. Just like you do at home when you're cooking cookies for the bake sale. Like, well, I need 500 cookies. Well, then you're going to look at the box, and the box makes 50 cookies. You're going to multiply the recipe by 10, right? You can bump everything up. We do the same thing in the chemistry lab. Right? Now, what really typically happens in a chemistry lab is that we are concerned about that number. How much stuff am I going to make? That's the whole point of chemistry. I want to make something. I want to do something cool, right? I want to end up with something I can use. I want a product. And so, with that amount, say, hey, am I happy? Am I not happy with that? Let's bump up the recipe. Let's half the recipe. Let's do whatever we want to do. Okay. Which is where we're going to go very soon. Wednesday, we are going to do a series of reactions, and we are going to try to calculate how much stuff should we be making based on our recipe. Okay, and then we're going to see how close we are. We're going to see how close we did it. So if I measure out 48.6 grams, and I do not make this much magnesium oxide, something must have went wrong with my lab, right? Now, granted, will chemists ever get 100% perfect? Probably not. But we want something close to 90.6. Might be 90.3, 89.8, or whatever. We'll want something close to that number. Now, while I got your attention, not really, but the oxygen gas. When you guys did that reaction, did you go measure the oxygen and make sure it was in there? No. The oxygen gas is just in the air. So we don't need to measure the oxygen. We just need to make sure that there's at least 32 grams. And then the magnesium will tell you when you're done, because it'll be done. It'll stop reacting. Okay, so we can have what's called an excess of oxygen. But it will take at least 32 grams of oxygen reacting with 48 grams of magnesium to make the product. All right, anyways, I'm going to shut up, let you guys go to work. That's a little bit further ahead than we needed to go, but that hopefully makes sense of why we do what we're doing. And it'll make a lot more sense on Wednesday when we do the actual lab. All right, I'm going to stop recording because I know.